Okay, I always like showing people cool and neat ways to see things. Here we have a 1-inch N48 Gauss neodymium iron boron, chrome plated. Now what I have marked here with a Sharpie marker is the plane of inertia separating out either pole. Now as I've told you before, in probably over 100 different videos, a magnet does not have poles. Well, of course it does. A magnet has a north pole and a south pole. No, it doesn't. Actually, as Faraday specifically called magnetism, he called it the dielectric field. The loss of inertia, which exists at a known rate, which was my discovery, 1/5 to the power of -3, which is an expression of the loss of inertia, which follows the golden ratio, expression of that loss of inertia. If we take inertia as 1, what is the rate of the loss of inertia? It follows the rate of 1/5 to the power of -3 over a given period of time in effective change. Maxwellian field equations dictate that all expressions of fields, now no Maxwellian field equation, of which there are 4 primary ones, have never defined what a field is. They are only expressions of what a field does, in effect, at a vector over a given period of time. Now I don't know if you know what electromagnetic induction is, but I assume you know what an AC or DC generator is and what it does. Obviously we actually have a rotating magnetic field against a dielectric plane of inertia, i.e. copper windings which generate power, end up with AC current, Tesla's serious invention of the AC generator. The only thing that actually an AC generator does is we actually have mechanical motion driving a magnetic field around a plane of inertia, which actually generates power. An actual AC generator is nothing other than a magnet inside out. We actually have the plane of inertia existing exterior to the magnetic field. So what all power generation is, in its absolute most simplest divine definition, is a inverse magnet, a magnet turned inside out. What would be a magnet turns inside out? That doesn't make any sense. Well, we actually have counter space as the plane of inertia, and we actually have at the center of an AC generator, DC generator, we actually have the rotating magnetic field, which of course is inverse to how Mother Nature works. You alternate that over a given period of time, you have change, in which we have induction. This would be a great example of induction. I just wanted to show you a neat little way of imagining induction, and also showing the plane of inertia. This is just a magnetic viewing film. Here you're actually able to see 2 lobes that define the polarity that is magnetism. You actually see that underneath the magnetic viewing film. I thought I would show you this neat little toy. You remember these toys? You'd actually place your hand underneath them. Excuse me, you're actually able to see something underneath the pins. There we go. So what I'll do is actually lift this up. I'll show you the pole, then I'll give you an example of induction and the difference it makes in changing the rate of induction over a period of time. I'll actually change the induction slowly, or I'll change it quickly. And I'll show you the difference that actually defines induction. Just using this simplex old analog toy, which is nothing other than little pins that have actually had their pointy ends cut off. So now they're just flat pins inside of a plexiglass case. Everybody's seen this stupid toy, right? Everybody's seen it. So what I'm going to do, I have the plane of inertia here, 1 pole here, 1 pole here, and like I said, a magnet does not have poles. It has the inverse of counter space. I'm going to actually shake it up, and then we're going to see, and mirrored in the pins, the plane of inertia. So all I'm going to do is hold it here, and then I'm going to give it a shake. Okay, now if you see off to the side here, you'll see that these pins along the plane of inertia did not rise. However, they did along the poles. You see that? Let me do that again. Okay, reset it, huh? Place it here, give it a shake. There, you're able to see it. Now, if I do it the other way around, give it a shake along one of the poles rather than the plane of inertia. The plane of inertia is now here. Here you can actually see the huge difference. Okay, now all Maxwellian field equations specifically and as analogous to induction, what would we be talking about in a rate of change over time? Okay, let's take a look at the radical difference. Now the quantification of the field applied and the proximity applied will be the same. So the quantification will be the same, but the quality will be totally different in the 2 things I'm about to show you. So now you have to ask yourself, and this gets back to the 4 Maxwellian field equations, if there's no difference in quantity, what is the qualitative nature of the change that defines the induction or the acceleration of these pins. There's no such thing as magnetic repulsion or magnetic attraction. There's actually dielectric convergence and the loss of inertia. There is dielectric acceleration, and there's a loss of dielectricity, which defines the denotation of magnetism. So since there's no quantitative change in what I'm about to show you, only a qualitative change, and we're actually able to apply a time-varying factor, what we have is electromagnetic retardation. We're actually able to apply that to the four Maxwellian field equations and to induction, by and large, both specific and general. So let's take a look at the difference just using this simple child's toy. As I slowly approach the pins, then I'm going to show you the result slowly. Okay. Now do you see how many pins are there? I don't know, maybe 10 or so. You're able to see it. Yeah. Okay, now we're going to have the same quantification of the field applied, since it's obviously going to be the same distance, but now we're going to change the qualification by altering the time variable. Okay, this was very slow, right? Very slow. We just have a few pins there. Now we're going to change the qualification by changing the temporal variable. Time. What will that do? It seems like a lot more pins are raised there. Now I know what you're thinking. You're thinking, well, what you actually did was shake the pins up and you gave them a bit of a head start, so let's not actually shake the thing as much. I know what you're thinking. You're almost slightly right, very, very slightly, but you're still wrong. So let's do it again, quickly, but without causing such a shake. Okay, there's no real shake. There's no shake applied there, yet we have, easily 6 times as many pins accelerate to the quote-unquote pole. Okay, that's not magnetic attraction, that's dielectric acceleration. That's ferromagnetic induction. This is the temporal variable in Maxwellian field equations using a simple child's toy. Okay, I did not shake it that time. Okay, let's go slow here. There is no difference in the quantification of the field applied nor the distance between this and the fast acceleration applied of this 1-inch cube magnet to this child's toy. Yet we have X number of pins here, and we have the same quantification here, but a different quality, which is a temporal variable, but time is not a thing in and of itself. This is the huge mistake of general relativity, is thinks that time is something that does something. Tesla specifically said that time is not a thing. Time is not a principle. The ancient Greeks, thousands of years ago, figured this out. Time, just like space, has no property. Time is nothing other than a measure of magnitude. But we're going to change the quality of the approach, but not the quantification, i.e. the field strength, the Gaussian strength applied. The only thing we're going to change is the quality. Okay? So if we have the same quantity applied at the same distance, how does the quality, i.e. the temporal variable, apply to induction? Okay, now fast. Do you see the difference? We have 4 or 5 times as many there as we do here. You see that? That's next to nothing. Slow, fast, slow, slow. That's the same Gaussian, it's the exact same Gaussian quantity at the exact same distance. Now, a field does not have quantity. I'm talking about the actual Gaussian flux here. So ultimately, we're not talking about quantification as far as the phenomenal sense, but this is exactly the same. Same distance, exact same field applied. Now we're going to change the qualitative factor as applies to all induction, to all power generation over a given period of time, as is necessitated with the denotation of electromagnetic retardation and induction, that if you change the temporal variable, you will affect the output. You will affect the resultant change. The quantifiable change, we have quantifiable change through a qualitative change in time. Do you understand the importance of that shit? Process that in your brain. Merely by changing the qualification, which is time, which itself is not a principle. Time is only the measure of magnitudes. Merely by changing the qualification, the temporal variable, we change the ultimate resultant quantification, the resultant phenomenal and existential and totally real effect. Well, if time is not real and we only change the qualification, i.e. time, then how can there be a true resultant quantifiable existential phenomenal change? That is the answer that I have solved. I will leave that for the 4th edition of my book, which is totally free, Uncovering the Missing Secrets of Magnetism. Okay? Descriptions are not explanations. I've made so many videos on magnetism, and someone will give me a pathetic description that they read out of some book or something that they were parroted to be told back in college or high school. That's a description. You know, I tell people that. I said, you've just parroted to me a damn description that some idiot told you that they read in a book and the person before them read in a book. That doesn't give you any place to tell me what the hell is going on, because what the hell is going on is what we call an explanation. And idiots that only have descriptions are not explaining what is going on. Since time is unreal and the only thing we've actually changed is the qualitative vector, the qualitative property of the approach and the induction. Very fast, look at the result. Very slow. We have the exact same quantity, but we have a different result and effect. The only thing that was changed is the temporal variable. Slow, fast. Slow, fast. You see the difference? Now you can describe to me all you want what is going on here, but you're not going to be explaining to me what's going on here. Okay? Let's take a look at the magnet again as I shake it along the plane of inertia. Remember, right now we're looking at the plane of inertia. You can see it right here underneath the magnetic viewing film. Okay, let's give it a little shake. Actually, let's do a little bit better than that. Let's give it one hearty shake. Plane of inertia. You see this null point right here? Let's do it again. There we go. We got a better one. You see that? A lot here, nothing in the middle, and a lot here. At the center of magnetism, there is no magnetism. Well, that doesn't make any sense. It's the same reason if you're able to sit inside of a capsule inside the center of the Earth, there would be zero gravity. At the center of any divergent field modality, okay, at the point, the null point of acceleration, there is not that which initiated the acceleration. The only way anybody could understand field theory in complete and totality, as Eric Dollard and Nikola Tesla said, is you have to understand counter space. Doesn't matter if you called it counter space, doesn't matter if you called it inertia, doesn't matter if you called it ether, doesn't matter if you called it 0 point. It doesn't matter what you want to call it. Mother Nature doesn't give a shit what you call it. She has no name for it. I've called it counter space. Other people have called it interspace. Other people have called it null point. Some people have called it the ether. Some people have called it 0 point energy. I've specifically referred to this line as the plane of inertia. It doesn't matter what you call it. Modern science calls this line right here the block wall. Guess what? I have every book ever written on magnetism. Every damn book ever written on magnetism. Every damn one. And there is not a single book anywhere that will tell you what the hell the block wall is. This is specifically a plane of inertia. If they want to call it a block wall, that's fine. I don't care what they call it, but they've never explained it. They have no idea what it is. They will talk about how it influences this, how it influences that, but they've never, ever, ever, ever explained what the hell the block wall is, i.e. the plane of inertia. I have explained it in the free book, Uncovering the Missing Secrets of Magnetism, which, by the way, is a free download, free, off of archive.org and other places. I never thought a book on field theory would garner so much incredible amount of attention, but it has. And rightfully so, because everything I've said has been logical, it has been provable, it has mirrored every known observable phenomena of magnetism. What humanity knows about magnetism is extremely minuscule. But anyway, I thought that at the very least I would use a pathetic child's toy to show you something that modern science has never been able to explain. They haven't. Maxwellian field equations, of which there are 4, have never given existential denotation to what a field is in principle. Saying what a field is only as a resultant of a vector over a given period of time as measured in an effect, such as induction and other things, that does not tell you what the hell a field is. Absolutely no damn way. That does not tell you what a field is in principle. Here ended the lesson. Wisdom above all else, lux e veritas. Bye.